Today we're going to be learning about electricity. Electricity is the movement of electrons. Electricity is an invisible force that can be used to provide light, heat, sound, or motion. At the simplest form of matter is elements. You learned this back in middle school and also in chemistry class. Atoms are the smallest piece of element containing all properties of that element. On the right-hand side, here you can see this is a model of the atom. In the center, this red and blue mass is the nucleus, and then on the outside, these little green things are representing electrons, which is spinning around the atom. So those electrons are what cause electricity. This image that you see on the right is an example of a model of an electron. Electrons are made up of, in the center, a nucleus, which has both protons and neutrons. In this case, the protons are represented as positively charged particles. They're red in this diagram, and the neutrons are represented as blue. Those are the uncharged atomic particles that are all in the nucleus. The atomic number of each element is equal to the number of protons that are in the nucleus of an atom, and that's the atomic number is what identifies the element, what makes carbon what it is, what makes hydrogen what it is, etc. In this case, we've got how many? 1, 2, 3, 4 protons. Okay. Electrons are these red parts of the electron. They're negatively charged particles that in this particular model are orbiting or spinning around, okay, the nucleus. And these are what we call orbitals. The valence electrons are the ones on the outside. Those are the freest ones, for example, here. Those are the freest ones. Those are the easiest ones to release and be able to run around a circuit to produce electricity. A lot of this information that you're seeing in these couple slides are things that you learned in chemistry. You don't necessarily need to know for this particular class, let's say for a test or for your final exam, but it's useful information to know. In this particular model of an atom, we're representing, these are the inside orbits, okay, and then these are the outside orbits. As you go farther and farther out, these outside orbits can fit more and more electrons. The orbits that are closest to the nucleus are ones that fill up first, and the ones on the outside, okay, are the ones that are freer, they're easier to go ahead and be released, in some cases, from the atom. Atoms like to have these valence electron rings full. Okay. For example, there's only one here, or empty. So I like to have them full. Let's say we're empty. For this example, this is a copper. Copper has one electron. It would rather give up this one, so it's really easy to get rid of it. So that one's really easy to leave. That's what makes copper a really good conductor. That's why we use it a lot in wires for electricity that, let's say, run through your home or run through the wires at school. In this case, as we said, there's one valence electron. So copper is a very good conductor, okay, again, because it's able to release that electron. Sulfur, on the other hand, okay, you probably learned about sulfur if you took earth science. It's that yellow one when you learned about the minerals, the yellow one when you scratched it, it smelled like rotten eggs. It's got 1, 2, 3, 4, 5, 6 electrons in the valence shell. Sulfur is not a good conductor. It's not a metal. It's a good insulator because it would prefer to fill up the valence shell, the outer shell, instead of releasing them. Basically, what electrons do is they jump from one orbit to the next. So they'll jump from one copper atom to another copper atom that's nearby, and that's what causes. And then it'll go ahead and knock the next one. And that's what causes So let's go ahead and run this animation here. This electron, see, one electron jumps from the first copper to the next one, to the next one, to the next one. Basically, essentially, that's how electricity flows from one copper atom to the next one throughout a copper wire. Conductors are described by materials where electrons can flow easily, and typically metals. Insulators are things where electrons don't really flow very well. Electron flow between atoms is very difficult. All right. Conductors tend to have 1 to 3 valence electrons. Insulators tend to have a lot more. And good examples of conductors are, again, metals: silver, copper, gold, aluminum. Good insulators: mica, glass, and quartz. Okay. Again, metals are the best conductors. Insulators, in this case, plastic is what we usually use for insulation on electrical wires. An electric circuit is a system where we have some conductors and components that form a path for electrons to run through, for electrons to flow. There are three properties that make up an electrical circuit. Something called voltage, which we measure in volts. Okay, when you talk about a 9-volt battery, let's say, that volts is telling you how much electricity can potentially be energy there is, or potential difference can be stored inside the battery. Current, which is measured in amps, and for amps we use the letter A to represent amps, B represent volts per volt. Current is basically how fast the electrons are flowing, and resistance is measured in something called ohms, and we use this Greek letter omega to represent what resistance is. Flow of electric charge is measured again in amps, so how fast it's flowing. And let's relate the flow of electrons to the flow of water. If we've got a water tank here, we've got a pipe that represents, let's say, watering. The tank would represent battery, where you've got electrons that are stored. When the faucet's off, okay, is there any flow? Of course not. There's no water flowing because the faucet's off. Okay. When we switch it on, all of a sudden now water can flow. Again, just like when we turn a light switch on, then all of a sudden electrons can flow, and then it'll turn the lights on for us. So again, for example, here our switch is off, our light bulb does not light up because there's no current. When there is current, electrons will go ahead and flow through the circuit. Now, electrons, if you remember in chemistry or middle school, you should have learned that electrons are negative. Okay, so the electrons are in the negative side of the battery. And electrons are attracted to the opposites. As we say that opposites attract when it comes to opposite charges attract. So these electrons that are hanging out in the negative part of the battery, the electrons want to start going to positive because they're attracted to positive. So they start running through our wire. They continue running through our wire. And then all of a sudden, when they get to our light bulb, they run through a circuit which heats up and emits light. And then once those electrons are done emitting that light, then they'll go ahead to the positive part of the battery, and then they'll kind of sit there. And once most of the electrons are gone, then the battery will basically not have any more stored charge anymore, and it'll stop working. Then you need to recharge it if it's rechargeable, or toss it out and replace it if it's non-rechargeable. Electron flow, again, is what really happens. The electrons flow from the negative side to the positive side. Okay. But before they knew what an electron was, this is hundreds of years ago, they thought that what was actually flowing was positive charges were flowing. So that's what we call conventional current. So the flow of positive charge is actually what we measure inside a circuit, even though it's not protons that are moving, even though it's really electrons that are moving. When people learned about electrical charges and electricity, as you probably remember learning, Benjamin Franklin discovered electricity. Well, they thought that it was positive charges that were moving because they didn't know what electrons were at the time. So what they said was current is the flow of positive charge. So when we measure current is actually going from positive to negative, okay, which is the opposite of where electrons flow, but that's okay. We just need to, and because we've set up a standard that's kind of going from positive to negative, okay, we're always, when we talk about current, we're always talking about flow of what a positive charge would do, which is really the opposite of what we know. But once they set up the standard, it's too difficult to change, so we just kind of stick with the standard that we currently use. Voltage, okay, is the pressure that causes current to flow. Again, we measure it in volts. Okay. Again, when the switch is off, is there pressure? Yeah, there's pressure there because water wants to flow. Okay. pressure is there, okay, but it's just not ready to flow yet. When the faucet is switched on, is there any pressure? Yeah, there's still pressure that flows, okay, when the water is flowing, just like when electricity is flowing. In a circuit, again, the battery is providing voltage that will push current through the bulb when the switch is open. Resistance is the thing that opposes current flow, okay, and we measure that in ohms. What happens to the flow if a rock gets stuck here in our pipe? If a rock gets stuck, okay, the flow decreases. It's kind of like if you, or if you were to go ahead and put your finger over a hose. Okay, you get less water coming out. Water does come out, squirts all over the place, right? But you get less water coming out. Okay, so the flow decreases. That's what we call resistance. You can think of it resistance as in a football game, the linebackers that are resisting you trying to bring the field down the hill. Resistors are things in a circuit that create resistance, okay? And it's whatever uses up the electricity. So for example, this light bulb is what's using up our electricity from our battery, so the light bulb is a resistor. The wires have a really small amount of resistance. It's negligible, it's almost nothing. So the real largest resistance in the circuit is really a light bulb. So if we reduce the current so that fewer electrons can flow, okay, then the bulb becomes dimmer. That's kind of like the dimmer, what we call potentiometer that you might have on your lights at home. You may be able to go ahead and have a little circuit where you can turn the lights down so they're not so bright. What that does is that changes the amount of resistance so that less current flows, so then the light is not as bright. When we're measuring voltage, we use this device over here, okay, that's called a multimeter, okay? And we're using it on volts. You'll see right here, this switch is pointed toward V, which is voltage, okay? We set it to voltage, okay? For a 9-volt battery, typically we want to set it to typically 20 volts. Most meters usually have a 20 volts, and we want to use DC. DC is the kind of electricity that's stored in this kind of battery. AC, which is this one here, is what comes out of the wall. So what we would do, okay, is we go ahead and measure across the component. So we take these red and black wires and we put them on opposite sides of the battery, okay, and that will go ahead and give us a reading and tell us, we read our dial here or our meter here, and it'll tell us how much electricity there currently is. We could also do the same thing across the switch. We could also do the same thing across the resistor, or we could even do it across this little LED light bulb. Again, this object is called a multimeter. Okay. Actually, all 4 of these are different types of multimeters. The one that we have is more similar to this one over here. We use those to measure both voltage, current, as well as resistance. That's why, hence the name multi. To measure current, we need to go ahead and put it on amps, okay, which is A. A is for amps. Again, we're dealing with DC amps. It's coming out of a circuit like this with a battery. We're going to set it to very small because there's very little current in this particular circuit. We actually have to break the circuit. Okay, so what we have to do is we have to break the circuit. We remove a little bit of wire, so that way the electrons are going through the meter. So the electrons are going from the red wire, and then they're going into the meter, and then they're leaving the black part of the meter and going back over here, and then they're going from there into the resistor. To measure what's called resistance, again, that's how much the device is fighting the electrons or slowing down the electrons. We want to set it to ohms, and this is the symbol for ohms, so we set it down here to ohms. Looks like here we have it set to 220K or 20 kilo ohms, K meaning 1,000, and then we measure across the component. Okay, and power must be off, so we need to have the switch needs to be off in order to measure resistance, or we can remove the battery, and then we just put it on either side. Put the black and red ones on either side, and it'll tell us what the resistance happens to. Ohm's law, okay, tells us that the current, or how quickly the electrons flow in a resistor, varies in proportion to voltage applied. So if I have more volts, then it's going to have a higher current. So if I were to go ahead and change my volts from a 1.5 volts, which would be typically what we call a 1.5 volt battery, normal AA or double A battery, let's say, or even triple A battery. We'd go ahead and put two of them together. That would give us 3 volts. So that would double the amount of current. Current is also inversely proportional to the resistance. So if I increase the resistance, then current will go ahead and drop. And think about it again. If you increase the number of linebackers on a football field, then it's going to be harder to bring the ball across to the other side of the field. So it's going to increase resistance, and there's going to be less flow. Okay, think of it that way. All right. So if we know two of those things, V, I, and R, V is voltage, I is current, and R is resistance, then we can solve for the other two. All right, so the formula is V equals I times R. Voltage equals current times resistance. Again, current is proportional to voltage and inversely proportional to resistance. V equals IR. We can also write it as I equals V over R, so we just go ahead and divide both sides by R. We can also write it as R equals V over I. Basically, it's the same formula, just written 3 different ways. You may have learned the density triangle. This is an example of the density triangle, but using Ohm's law. Okay, well, let's say we're solving for V. What we want to do is we want to put our thumb, cover it on top of V, and then V is equal to I times R. Okay. Let's say we want to solve for I, then we're going to put our thumb on top of I. So I is going to be V divided by R. Let's say we're trying to solve for R. So then we put our thumb on top of R, so R is equal to V divided by. So here we've got a flashlight, and the flashlight uses 6 volts in this battery. So it's got a bunch of batteries together. And it has a resistance of 150 ohms. When the flashlight's on, how much current is drawn from the battery? So first we want to write down the things that we're given. We're given that voltage is equal to 6 volts, right? And we're also given that resistance. For resistance, we use the letter R. So R is equal to 150 ohms. All right. So first we're given. All right. And then next we need to figure out what are we solving for. What's our unknown? Our unknown is current, which is I. So I is our unknown. So I is going to be R question mark. What are we solving for? All right. Now that we know that, now what's our equation? Well, we just said V equals I times R. And here's, this is what we call a schematic diagram, a pictorial diagram that represents what's going on. This picture right here represents a battery, again it's 6 volts. We write resistance as kind of like a little lightning bolt, this little squiggly here. Our resistance is 150 ohms, okay? And we're solving for electron flow, which is, for current flow, which is I. So, we're solving for I, so I equals V divided by R. And we substitute in, V is 6 volts, R is 150 volts, so we do the math, we get 0.04 amps. We can also write 0.04 amps as 40 milliamps. M is 10 to the minus 3.